Some basic, some standard rules I'll write without the derivations because they're available everywhere. You can go through them. After that, we'll do numericals again. I think we'll end this unit 1 introduction and errors and floating point representation today. And by the next class, we'll start with unit 2, which will be system of linear equations. Okay. So anyway, so some points about errors that need to be remembered. So some rules to remember. So this is pertaining to errors. Okay. So suppose you have any number x, and that can be written as 0 dot d1, d2, d3 into 10 to the power. Suppose you can do it, and these are decimal digits. D1 has to be non-zero. D1 is, well, I mean, it would be non-zero. Okay. So rule number 1. Absolute error due to truncation. Okay, so suppose we say that if xa is the truncated value, if xa is a truncated value, where truncation happens after k digits. Okay, so you've taken 4 digits, 5 digits, and then you truncate it. Okay, then it says that the absolute error will always be less than 10 to the power n minus. That's a rule. This is the rule. It's important. You can verify it in the problems that we'll do. So this is what will always be. All right, we'll do some numericals and you can also check. Okay. Then there is rule number 2. Relative error. Due to truncation. So again, if xa is the truncated value where truncation happens after k digits, that's the standard thing. So relative error, xa, x minus xa divided by x magnitude will be less than 10 to the power of minus k plus 1. This is how this error would go, right? So that's rule number 2. Then comes the third, rule 3, which is absolute error due to rounding off. Okay, so again we are rounding off to k digits. So if xa is rounded off, to k digits, then the absolute error, whatever you will calculate, will always 0.5 times 10 to the power n minus k. So you can remember it like this. For truncation, it is 10 to the power n minus k, and for rounding off, it is half into 10 to the power n minus k. So these are important results. And then rule 4 is that relative error due to rounding off. Relative error due to rounding off is x minus xa divided by x, which is going to be less than 0.5 into 10 to the power of n minus k. So this is the fourth result. And you must remember these ones. There is another thing that I would want to point out, and I would call it rule number 5. That is that if your solution, or if any value you want to be accurate up to n decimal digits, okay. So if a value is accurate up to n significant digits, well, that means after decimal we are talking about, in the normalized form that I've written about, n significant digits. If a value is accurate up to n significant digits, we must ensure we must ensure that the relative error is less than 10 to the power minus k. And this is actually probably a rule that you should be remembering once you're doing any program. Suppose you want your result to be accurate up to 5 decimal digits, so you should run the iteration at least to a point where your error that is coming out, relative error is at least of an order of 10 to the power minus 5, right? So this is an important rule. This is, I think, probably something that you will be using a lot when you're writing programs. So this is something that you should remember. Okay. So let's do some numericals, and in that we'll also see how these rules get reinforced. So let's look at some of the examples that we do. So the first example is that, let us say that x is 0.005998. Okay. Find the relative error if x is truncated x is truncated to 3 decimals. 3 decimal digits. Okay. So How will we proceed? The first thing is that we'll write x in the normalized form. Okay. So the normalized form would be 0.5998, and we could say 10 to the power of -2. Okay, because this decimal will go here and this will go here, so that means 10 to the power -2. It is now written in normalized form. You can see that your n is -2 in this case. If you compare it with this expression here that I've written, this expression, then n is -2. D1, D2, D3 are values here which are 599. Okay. Now when you're truncating it, so your XA, so you're snapping it at this point, so your XA becomes 599 into 10 to the power of -2. Okay. So your relative error, I would call it RE, is going to be X minus XA divided by X. So that value will come out to be can anybody tell me what this value would be? So it will be 0.0008 divided by 0.59 mod. Now what is this value? Can anybody tell me? Just need a calculator.
00133.
001
133
33.
556.
I'm sorry.
335 recurring.
So I think this is it, right?
Yes, sir.
So if you write this in normalized form, this will give you 0.133 into 10 to the power of -2, right? So this is your relative error. Now let's look at the rule. So relative error due to truncation is this, right? So relative error will be less than 10 to the power of -k plus 1, right? So we should have, the rule says that your RE should be less than 10 to the power of -k plus 1. And in this case, k is 3 because we have truncated it up to 3 decimals. So that means your RE should be less than 3 plus 1, which is 10 to the power of -2. It should be less than this one. And you can see that it is less than this value because this value here is less than 1. That means, so we know that, you know, 0.133 into 10 to the power -2 is less than 10 to the power -2, so it gets satisfied. So that rule, you know, is satisfied. Okay. I think if we go by another example, I think we did this example in the last class also. I'm not sure, but we'll see if the absolute error also satisfies the property. So let's look at this. So if x is 0.00, oh, sorry, just a second, 0.0045859. Okay. So now what you're doing is you're finding the absolute error. So the question is find absolute error if x is truncated to 3 decimal places. Okay. So let's just first write x. X is 0.45859 into 10 to the power of -2. So your n is -2. Okay. XA, it is truncated to 3 decimal places. So you have 0.458 into 10 to the power minus 2. Absolute error is going to be this quantity. And this will come out to be 0.0000529 into 10 to the power of minus 2. So if you write it in the normalized form, it will be 0.529 into 10 to the power of minus 5, right? And the rule says, if you look at the rule, which is rule number 1, it says that the absolute error should be less than 10 to the power n minus k, right? So, so absolute error should be less than 10 to the power n minus k, which is 10 to the power of minus 2 minus 3, which is 10 to the power of minus 5. And you can see clearly that this number is less than this, because this is 1 into 10 to the power minus 5. This is 0.529 into 10 to the power minus 5. So it is lesser than this, right? So this rule gets satisfied. So rule number 1 is satisfied uh, in this case also. So you'll see that this is always going to be satisfied. So you should remember these rules. They are going to be helpful when you're going to write the iterative codes and you have to come out. So you should see that, okay, there is probably a number which is coming out to be up to 4 decimal, 5 decimal, like this we want. So when should we ask our a program to come out? So these are some rules which are going to help you then, and you're going to be iterating through a number of steps and repeating it. So for how long will you repeat it? That will be determined by these rules 1 to 5. Generally we go for simple truncation. Uh, that is probably the most convenient. Doesn't matter if you have an error of an order of 10 to the power minus 5 or 10 to the power minus 6. It's pretty much giving you what you really require. So really hardly I see anybody going for rounding off. But rounding off, the errors are even lesser. Like half of all these errors. So you're again going down. But if you're at 10 to the power minus 5, it's pretty much okay. You don't really need to do zero point 0.5 into 10 to the power minus 5. It doesn't really matter. So I think truncation would do the trick, and you should follow that, right? Let's do another numerical. I would want you people to try to do it. So let's look at another example. After today's class, over the weekend, I think by tomorrow, I will put up some practice problems along with, I'll not put up answers straight away. I'll put up some practice problems that you people can practice. If you want to turn it in on Google Classroom, well, you do that, but it's not, it doesn't carry any marks, but it's going to be good practice because it'll give you an idea what kind of sums would be expected in the exam from this unit. And you should just know a little bit about the concepts that go into finding out errors and related things, right? So let's look at this numerical one. So given the solution of a problem as XA 35.24, okay, the relative error is 2%. Okay? Find up to 4 digits, up to 4 decimal digits. The range of values within which the exact value of solution must lie. नमस्ते नमस्ते देखिए हाँ यही रख दीजिए Okay. So this is the problem, and let's see if we can find out. So if the relative error is 2%, which means that your x minus xa divided by x should be less than 2 by 100. Okay? So if you remove the mod sign, so you get minus 2 by 100 less than equal to x over xa over x over 2 by 100. Okay? So you just need to solve this equation now. xa is given to be 35.25. So you will solve them two at a time. So first equation that we will solve is going to be that x minus xa over x is less than 2 by 100. And the second equation that you are going to solve is that minus 2 by 100 is less than x minus xa over x. Okay. So you solve them, you'll get two values of, you'll get two ranges basically of x, and then you have to combine them and you get an answer. So I'm waiting for you to tell me the range. What will be the range in which the exact value must lie? Is there anybody who could solve it?
So the
54
upper limit
point,
is 35693 or
I think this is
9694.
94, 55.96. So this is the range in which x will lie. Okay. So this is another example that you could do. Now let's look at some more examples of how things get added, subtracted, multiplied, when there will be an overflow, when there will be an underflow. Things like that. So we'll consider floating point arithmetic. We'll do some numerical. Of course, you've been doing that only, but let's look at some of the addition, subtraction, etc. In floating point arithmetic. Okay. So let's say that we have a hypothetical computer. Because we can't, I mean, if you look at practical computers, you'll have to have 32 bits or 64 bits, but we can't really do that kind of a calculation by hand. It will be absurd, take too much time. So let's look at let's assume that there is a hypothetical computer, okay, which can store normalized floating point numbers with 4-digit mantissa. Stores floating point numbers with 4-digit mantissa. Floating point numbers which are normalized. So I should probably write it here. Which means that your numbers would be something like this: D1, It can only store these 4 values. Okay. So this is your mantissa here. Okay. Normalize 4-digit mantissa, and let's say it can have a 2-digit exponent. Okay. So basically, what you have is that your mantissa can vary from minus 0.9999 to plus 0.9999. So this is going to be for your mantissa, and your exponents can vary from minus 99 to, so this is for your exponent, basically, right? So of course signs would require something, but we are not going too much into signs right now because we are only interested in seeing signs are getting stored in sign bits. You can assume that, and they are separate from all this. So let's see how we can do some kind of a mathematics based on this floating point arithmetic based on this hypothetical computer. So let's say I tell you add 0.5467 E5 to 0.7253 E2. Suppose I say this to you. Okay. So you have to tell me what will be the sum, right? So now you can see that this is 10 to the power 5, this is 10 to the power 2. So we really need to make it 10 to the power 5 here. So the best thing, this would become 0.0007253 E5, right? But we know that our computer can only store up to 4 mantissas. That means this value, these 3 values will just go away, and this number will become 0.0007 E5. Okay. So now when you add these two numbers, so it will be 0.5467 E5, 0.0007 E5. So you will get 5474 E5. That's your answer, right? So this is one example. Let's look at another example. Let's see. Question is you're adding 0.5467 E5 to 0.7254 E2. Sorry, it's not E5. Let's take it to be E2. So if you do this addition, can you tell me what will be your answer? Let's try it out. So you will do 0.5467 E2, 0.7254 E2. Okay. So this would be 1, this will be 2, this will be 7, this will be
1 1.
and 1, and
Yes,
E2.
sir. So the last digit will be removed.
But
It
now
will
what will
be
happen
3.
is, yeah, so what will happen now is that this is not the normalized form. The computer will not store it this. Computer will first convert it into normalized form. So if you convert it into normalized form, so this will go here, and you will get one more 1. So this will become 0.12721 E3, but your computer can only store 4-digit mantissa, so this will go away and your final answer will be 1272 E3. So this is how the computer will store this. Okay. The reason why one is removed is because your computer can only store 4-digit mantissa. So that's why it is removed. Let's look at another example. And it will be interesting to see what you tell me in this example. Suppose I say you add 0.5467 E99 to 0.7254 E99. Tell me, what do you think will happen? What do you think will happen? So when
So
you
it
do
can't
the addition,
store
yeah,
E100, so I think it will go to it will like there will be an integer overflow and we'll get
yes,
E
yes,
minus
yes.
9
Very
minus
nice.
9.
Yeah. So if you add these two numbers, you will get 1.2721 E99. But the computer is not going to store this number like this. If computer could store, the computer will be like 12721 E100. Okay, it will remove this and it would probably show you this. Should show you this, but this is okay. But the exponent can only be 2-digit, like I told you. So now the exponent goes to 100. Of course, the computer, this hypothetical computer, will not store it. It will say overflow. You will not see this. This is the same case. If I don't know if you've ever noticed, you can probably do it. If you multiply two exceedingly large numbers on your calculator, sometimes it will just call it error. It will just say E. The reason is that the outcome is not the outcome that is coming after multiplying these two exceedingly large numbers cannot be stored in your computer in calculator. So that's why it says error. Okay, so this is basically what overflow will be like. Um, Similarly, you can try some subtractions, and you can try some multiplications and divisions.
So
So yeah,
why can't the third digit of the exponent be stored?
why can't?
So like the third digit of the exponent be stored.
So we are taking a hypothetical computer that can only store up to can only store 2-digit exponents. I mean, if I'm taking a hypothetical computer, so it's not that it cannot be stored. Of course, you can store it in modern day computers, but I'm saying that we're taking a hypothetical computer that can store exponents only up to 2 decimals. If I would have said that you can store decimals up to, you can store exponents up to 3 decimals, so this would have been minus 999 to plus 999, and then this result would not have been overflow. This result would have been fine. But I'm taking a hypothetical computer. If you, I think probably uh, overlooked this thing. So this is, we are doing all this calculation considering that our computer is this, that can store 4-digit mantissa and 2-digit exponent only in this. So this is just a hypothetical case that I'm taking into this. If it could store 3, then you can obviously get a result in this case. I think probably now it should be clear. That you're calculating these things on some hypothetical computer that can take in 4 digits or 5 digits in mantissa and then take maybe 1 digit in exponent or 2 digits in exponent, something like it. If I would have said, that this hypothetical computer has only 1 digit exponent, then this would have been okay, this would have been okay, this would have been a problem. And even if you would have got a exponent like E10, that would have been a problem, because I've given you a computer that can store only 1 digit in exponent. So that is what it is. Okay. All right. So you can look into such problems. I'll give you some problems. I will not do those problems here today. I'll give you some problems on subtraction, multiplication, and even division in some practice problems that I'll give. Try it out, and for some small problems which are very straightforward, I may just give you answers also. But some problems where you'll have to apply your brain a little bit, perhaps you don't probably want to wait, and I'll give you an answer in maybe a couple of days time. So that's it. I think probably we'll end the class here today, and I'll see you in the next class. We'll start with the system of linear equations. I will also be floating a Google form today because I have organized a workshop on MATLAB, which is going to happen from 11 to 1 on Saturday. The MATLAB people have kindly consented to take it for 3 hours. It's basic MATLAB. So all you need to do, it's online. So all you need to do is fill up a form and show your willingness to join, because I need to send it to the MathWork people. And you learn basic MATLAB in it. You can install Octave. And yeah, sir, could you please look into rule 4? Okay, what is there in rule 4 that I wrote? Let me just see. I've stopped the screen sharing, but let me see. Yeah, okay, yeah. So yeah, thank you. So yeah, thank you for pointing it out. Just a second. Let me just show you what I wrote. It needs to be corrected. Thank you so much. So I hope my screen is visible now. In rule 4, I wrote that x minus xa by x should be less than 0.5 n minus k. It is not n minus k. It is actually minus k plus 1. Right. Thank you so much. Okay, so I'll be moving a Google form right now, like in maybe 5 minutes or something. And if you're interested to do the workshop, please fill it with your details, and a Zoom link will come shortly, and you attend that. Install Octaves on your systems. From next week onwards, we'll get into some linear equations and system of linear equations, methods of solving it, and we'll be doing some programs. So if not theoretical classes, we'll definitely have the lab classes offline. So we'll decide that day with mutual consent. And so MATLAB has also been installed in 25 computers in the lab, so you can access that also. And you can work with MATLAB if you have MATLAB, but I don't know whether you have it or not. But we have licensed versions here in the lab. And if you don't have a license, version, you can install Octave. Yeah. All right then. See you. Bye bye. Good day.